All right, so let's consider the following. Okay, so we have two systems. Okay, so system 1, it has n1 particles, and its single particle phase space is made of m1 cells in total, and we can do the same thing we did before. Okay, so we put it in an adiabatic insulation, and we are trying to find the equilibrium distribution of occupation numbers in these M1 cells of system 1 that will maximize its Boltzmann entropy. Okay, so that would write like this. So we are trying to find the optimal values for these guys here, and we would then repeat the exact same calculation that we have done up to now. So we would find that the equilibrium occupation of cell I in the system 1 is going to be the exponential of some Lagrange multiplier, alpha 1, and minus another Lagrange multiplier, beta 1, multiplied by the energy of each individual phase space cell of system 1. Okay, so this is what we would find, because that's already what we have calculated. And if we do the same thing for a second system 2, that has, it's the same box, maybe different volume or whatever, but there are n2 particles, the phase space has size m2, so number of cells m2, and the equilibrium macrostate in this case, let's just write it, a little bit tedious notation, but it's very simple. What we will find exactly the same thing, but with this different notation. So there would be some generally different constant, alpha 2, and some generally different Lagrange multiplier, beta 2, multiplying the energies of the cells in system 2. Okay. So what happens now if we take these two systems together and we put them in an adiabatic insulation? Okay, so let's do that. We have some insulation here, like that, like so. Okay, and we put the two systems here. I mean, they don't exchange any particles, so still we have they are closed systems, so we have n1 particles in this side and n2 particles in the other side, but they can exchange heat. So this is not an insulating wall in between the two systems. And so then we are going to try to find what is the equilibrium occupations for this joint system made of the two subsystems in thermal contact with each other. So which are the constraints? I just said now that the total number of particles is constant. So the particles of the occupations of the cells of system 1 are going to sum up to the total number of particles of system 1. And the same thing happens with system 2. Okay, so if I sum over all cells, I get n2. Okay, and then the other thing that needs to happen, because there is an adiabatic insulation which is encompassing both subsystems, what we have here is that the total internal energy, which is U1 plus U2, which itself is, the sum over the cells of the first system of occupation times energy, occupation 1 times energy 1, plus the same thing for the second system. You see, very tedious notation, but very mechanical. What I'm doing nothing really. So this thing, I, epsilon I2, okay? And then the whole thing is a constant, okay? Just like this is a constant, and like that it's a constant. Okay, so what we want to do is to find what is the distribution of occupations that is going to maximize the statistical entropy of the combined system. So remember that when we combine systems, the statistical weight of the combination is the product of the statistical weights of the first and the second. Okay. Now these statistical weights, we saw the expression for them with the combinatoric method. They are identical. The only thing that changes is there are different sub-indices in the m and in the n's. Okay. So we already know what the logarithm of such thing is going to be. No? The logarithm of the that would be the Boltzmann entropy divided by k, which is just going to be the logarithm of the statistical weight of the macrostate is the logarithm of the product of the statistical weights, and this is just the sum of the logarithms. Okay, so omega 1 plus omega 2. Fine. And then these things we have calculated them already, right? It's the same expression we know. For the first one, we will have n1 logarithm of n1 minus the sum from 1 to m1 of ni1 logarithm of ni1. Okay, and for the second one, it's the same thing, exact same thing, but with the subindex and superindex 2. Okay, so plus, here it is, same thing. So this is a 2, and this is a 2, and this is also a 2. Okay, so you see. Fine, and this is what you need to optimize. Okay, so you need to use again the method of Lagrange undetermined multipliers to find what occupations here and there maximize this object. Okay, the statistical entropy of the combined system. So what you do, once again, the same thing. You differentiate or take virtual displacements on the thing, right? So this stuff, which I wrote here, and I'm going to write it explicitly. And then you have to add the constraint. So remember, first constraint is the number of particles of system of either system is constant. So we can put here gamma 1. And here is the total number of particles of system 1, and here is the sum over the occupations. Okay. And the same thing happens with the other system. So you have n2 minus the sum from I to m2 of ni2. This is 1, by the way. And we have now another constraint, and this is the energy constraint. But we have only one multiplier, because we don't have a constraint in the energy of subsystem 1 is constant and the energy of subsystem 2 is constant. Now the global energy is constant, but the individual energies can't change, okay, because they are exchanging heat. So this is the key point. Okay, so here we have u1 plus u2 minus the sum from 1 to m1 of ni1 ei1 minus sum, so the contribution to the energy of the second part, ni2 ei2. Okay, that long expression has to be equal to 0. Okay, that's what you do to apply Lagrange undetermined multiplier method. Okay, and what you get here is very unsurprisingly that the equilibrium occupations for subsystem 1 is going to be of this form. Okay, and here you have beta ei1, and here in the second one you have i2 e to the minus alpha 2 e to the minus beta ei, sorry, epsilon i2. Okay, so you see, before you put them in thermal contact, you had the same thing, but here you had a different beta 1 and beta 2. Once you put them in contact, the equilibrium configuration that comes out of Lagrange undetermined multipliers turns out to be something where the two occupations of the two different systems share the same beta. So it does make sense to think of beta as the inverse temperature. Okay, so that is consistent. That is something reasonable to think. Now we will see the last little bit of evidence that we need to convince ourselves. Okay, and this is also the equation of state of an ideal gas. So remember again the expression for the Boltzmann entropy in the equilibrium configuration. Let me see if I get it right. So there is a Boltzmann constant, there is n logarithm of n, then there is the alpha n, and then there is the beta u. Okay, that's the expression we found before for a single system. So now let's differentiate this, but in this case we are going to be more careful when differentiated than before. The first term is still constant, so we don't put it. This is the alpha times n plus beta du plus u d beta. And remember what we had done before. Okay, so for the alpha we had said that this thing, yes. Well, okay, let's just write what we said. So what we had said is that okay, you have n, and n is the sum over 1 to m of e to minus alpha e beta ei. Okay, and then we took logarithm of this thing, and then we took the derivative of that. And when we did that, or we rather differentiated that. So when we do that, we get 0, we get minus the alpha, and then we have to deal with the logarithm of the sum of these terms here and differentiate that. So what you get is the 1 over the sum, that's the differential of the logarithm, e to the minus beta ei, and then the derivative or the differential with respect to beta of this exponentials, right? So in the exponent we have the sum and a minus beta, so that's why the minus sign is coming there. And here the derivative gives me this constant ei, and of course it's an exponential, so you also get the same exponential which you differentiate, and here is d beta. And before we just left it like that, okay, but I told you that arguably there would be an additional term, okay, and I'm going to write this term like this. So this is the change in the sum itself, okay, and this change, so imagine that, you know, I do a process and I think of a process, that's what the differential thing is, it's just an infinitesimal process. I think that the sum will change from this, well, let's just say that the sum of my system, if the volume does not remain constant, I have a sum over phase space cells. If my volume changes, the number of phase space cells that will exist, because they are all the same size, because I fix the size of the space phase cells, if there is more range available for, say, the coordinates of my system, because they can occupy a larger volume, then there will be additional cells appearing in my sum. So this thing will turn into a sum from 1 to m of e to the minus beta ei, plus, and there will be an additional little sum here from m to whichever m plus delta m there is of e to the minus beta ei. Okay, so this additional term is what I am somehow representing by this differential of the sum. So that's a change in the sum. Okay, and because it's a differential of a logarithm, there is a differential of the sum divided by the sum. That's the same that is appearing here. Okay, but instead of differentiating with respect to beta, I'm differentiating with respect of the sum itself, or if you like, with respect to m. Okay, and just hand wavily, okay, I'm not going to be very accurate here, but let's say that the relative change in the sum is going to be the same as the relative change in the volume. It has to be, okay? If this change is coming from a change of volume in my process, then this has to be the case. So that when I write differential of alpha, what I'm writing is minus the internal energy, remember, divided by n d beta. This is this term here, plus this additional new term. Well, I'm just going to write it like this, differential of volume divided by volume. Okay, so let's insert this into the expression we had here. Okay, so the expression we had here, let me just copy, bring it down here, and put it there. Okay, so what I have is well, just that, right? So let me just use, oopa, what happened? Oh, there it is. No, it isn't. Let's just move it like this. We'll remove that. Now we'll write differential of alpha, just copying from here. Okay, that's it. That's differential of alpha, and it's the whole thing is multiplied by n. Okay, so just remember this is the n multiplying it. Okay, so this is the expression, and you can quickly see that this u dv, which is a negative sign, is going to cancel that when you multiply by n. But now you get two terms. You get this n dv divided by b, and you get beta du. And once again, we are going to compare with the fundamental thermodynamic relationship in terms of the true thermodynamic entropy. Okay, so ds, remember, is 1 over t du plus pt dv. And what we get from this Boltzmann thing, when we allow the volume to change, is vita du, and now get n dv v. Okay, so somehow this n divided by p is this pt. Okay, so pv is I'm forgetting something, which is the Boltzmann constant multiplying, right? So let me just see what it is. Yes, I just completely forgot about it. It's just here. Okay. So this Boltzmann constant, let's say it's dividing here, right? So when I write the thing, I have the Boltzmann constant here and also there. Okay. So what I repeat is this kn divided by b has to be equal to pt, just in the same way that we've said before that k beta has to be equal to 1 over t. So pb is n, well, k n t, and this is the equation of state of the ideal gas. Okay, so we recovered also the equation of state of the ideal gas. So everything is being very consistent. Okay, so we did a series of sanity checks, and what we have somehow became comfortable with is that this Boltzmann entropy, at least in the case of non-interacting ideal gases, happens to be equal to the true thermodynamic entropy, and we can arrive to the same thermodynamic consequences and relationships from a completely different standpoint of statistical mechanics.